Our next couple of weeks are going to cover matrices and matrix algebra, and it turns out that matrices are really founded upon this idea of solving systems of linear equations. So this should hopefully be a review for you, at least this section 4.1, which is we're going to be reviewing systems of linear equations in two variables. So a system of equations is just a collection of two or more equations. I've got a couple of examples behind me. Here's example 1. I've got two equations here, 2x plus y equals 5, and minus 4x plus 6y is minus 2. So there's an example of a system of equations. And here's another example. I've got x plus y squared equals 5, and 2x plus y equals 4. That's also a system of equations. However, what we're going to be looking at is systems of linear equations. And this is not linear because I've got this squared term here, right? In the first example, both of these are linear equations. They're graphs, they're straight lines. Meanwhile, even though the system has a linear equation in it, the second one, 2x plus y equals 4, is a linear equation. They're not all linear equations. So we're not going to be looking at stuff like this. This is not linear. And then I've got a third example here, x plus y plus z equals 6, 6x minus y plus 4z equals 0, and x minus y equals minus 3. That is, again, a system of linear equations. Everything in this is linear. But in this example, I have three variables. There's nothing wrong with that. We'll move on to three variables very soon. It's just not our topic for today. We're going to be looking at systems of linear equations in two variables. And what we want to do is we want to solve these systems. So what do I mean by solving them? Well, what I'm looking for is I'm looking for a value for x and y that satisfies both equations simultaneously. Right, there will be lots of values for x and y in this first example. You can find lots of different values for x and y that satisfy this first equation, but I need them to satisfy, when I plug in my value for x and y, I need it to satisfy both equations at the same time. Alright, so a solution of a system of linear equations, or really just any system of equations, doesn't have to be linear, but a solution of a system of linear equations consists of values for the variables that satisfy each equation in the system simultaneously. Okay, so for example, let's see, for example, I'm going to claim x equals 2 and y equals 1 is a solution for system number 1. So we'll go ahead and we'll check these out. Let's try plugging in x equals 2 and y equals 1. We'll just do this mentally. If I plug in x equals 2, I've got 2 times 2 is 4, plus y equals 1, 4 plus 1 is 5, does equal 5. So great, it satisfies that equation. But there's lots of other values for x and y that also satisfy this equation. A solution has to satisfy both equations at the same time. So my claim is when I plug in x equals 2 and y equals 1 into the second equation, it also satisfies it. So let's see, if I plug in x equals 2, I've got minus 4 times 2 is minus 8, plus 6 times 1, minus 8 plus 6 is minus 2, equals minus 2. Great. So there is a solution. It turns out, for theoretical reasons that I'll get into in just a moment, that's the only solution. There's exactly one solution to this system, and I'll show you why in just a second, but you'll also often see these solutions sort of codified as a point, coordinates. So x equals 2, y equals 1. So you'll sometimes see them written like that. We'll sometimes do that, and I'll show you why right now. So in this particular case, where I'm working with, say, two equations with just two variables, remember that because these are linear, the graphs of each equation is a straight line. So if you were to graph them, here's sort of the three possibilities you could end up with. You graph both lines, and they look something like this, two lines that intersect. Well, they intersect at a single point, and that point corresponds to the solution. Because remember what we're looking for. We're looking for values that satisfy both equations at the same time. Well, every single point on the graph of the first equation is a solution to the first equation. Every single point on the graph of the second equation is a solution to the second equation. So the point where they intersect is the point that satisfies both of them at the same time. So there's the first possibility, and this will probably be the most common case. You end up with two intersecting lines, and this means you have exactly one solution. Or in other words, there's a unique solution to your system. This can happen too, though. You could graph both equations, and you'll find that they actually represent parallel lines. So every point on the first line is a solution to the first equation, every point on the second line is a solution to the second equation. Well, if they never intersect, then there's nowhere where you ever have a solution to both equations simultaneously. So this can happen too. Yeah, they represent parallel lines, and in this case you have no solutions. The terminology here is we often say it's an inconsistent system. So the solution's inconsistent and it has no solutions. And the third possible case is both equations, if you were to graph them, they might be written slightly differently, the equations are written slightly differently, but they actually do have the same slope and the same y-intercept, so they're the same line. So both equations actually represent the same line. So this is not just one line, this is two lines on top of each other. And that means when I'm looking for solutions to my system, well, every single point on this line satisfies both equations simultaneously. So in this case, you have infinitely many solutions. These two cases, case 1 and case 3, because they have solutions, this is the consistent case. So the terminology here is we often say this represents a consistent system. A system that does have solutions. And even though I'm sort of justifying this with just the two equations and two variables case, this turns out to be the case for systems of all linear equations. Doesn't matter how many equations you have, how many variables you have. This always happens. There's only three possibilities. Either your system has exactly one solution, a unique solution, it has no solutions at all, or it has infinitely many. In other words, it's impossible to have a system where you have exactly two solutions. Once you know you have two, well, that means you must fall in this case. There's actually infinitely many more. Alright, so this is what's going on, and this is what I was saying, by the way. This is why sometimes your solution is codified as a point with coordinates. Because that's really graphically what's happening. Your solution represents a point on the graphs where the 2 points, or where the two lines intersect. So anyway, let's get into what we really want to do, which is solving these systems of equations. Okay, so there's generally two ways that people solve systems of equations. The first is the method of substitution. I'm only going to do it once just because I want to remind you of how this works, how substitution works. But I'm only going to do one example because it only really works very well when you have small systems like this of just two variables. We're going to move on to bigger systems where we allow 3 or more variables. And in that case, substitution isn't really very good. But if you only have 2, substitution is fine. So I just want to remind you quickly of how this works. Let's give these equations names. We'll call these equations 1 and 2. Substitution is essentially choose any equation that you want and solve for one variable in terms of the other. So how about here, let's just solve for y, because y is sort of, it doesn't have any coefficients in front of it, so it's easy to solve for y in this equation. So we're going to solve for y in equation 1, and that gives me y is minus 2x plus 5. Okay, so now I've isolated y, I've solved for y. And here comes the term substitution. I'm going to substitute this into the other equation. So now, substitute into the other equation, into equation 2. So if I plug this in, I'm going to have minus 4x plus 6 times no longer y. I know y must be minus 2x plus 5. 6 times minus 2x plus 5, and that must equal 12. Well, now I have an equation involving a single variable x. I should easily be able to solve for x at this point. So we'll try to do that. We'll solve for x. I probably need to distribute this all out first. This is minus 4x minus 12x. 6 times 5 is plus 30 equals 12. Okay, we'll group things together. We've got minus 16x equals 12 minus 30. If I bring the 30 over to the other side, 12 minus 30 is minus 18. So x is minus 18 over minus 16, dividing both sides by negative 16. And that looks like I can divide top and bottom by 2, minus 2 in fact. So that's 9 over 8. And that's fully simplified. So now I know what x has to be. I know x has to be 9 over 8, so the third step, we'll call this step A, step B. So step A is solve for one variable in terms of the other using an equation. Step B is plug that into the other equation. And step C is now back substitute. Right, I already know x has to be 9 over 8. Let's just plug that into any old equation and solve for y now. Back substitute, I'm going to go with the first equation because it looks easier. It's got a smaller coefficient in front of x. So 2 times 9 over 8 plus y equals 5. That means y is 5 minus, what am I subtracting off? 2 times 9 over 8, that's 18. Oh, let's make this easier. 2 cancels with 8, makes that 4. So 5 minus 9/4. 5 is 20 over 4. 20 over 4 minus 9 over 4 is 11/4. So there's my solution to this system. So solution is x is 9/8, and y is 11/4. And again, the nice thing about this particular topic is you can always verify your solutions. You can plug them into your equations, and you'll find that they do indeed satisfy the system. So you're 100% guaranteed that this is correct, that this is a solution. And that is, of course, the only one. There's our unique solution. So this is substitution. I don't want to dwell on it, I just want to remind you of how it works, and there is this method for solving these systems. But again, it's not very good once you go to larger systems with more variables. So in comes the second method. Alright, a lot of writing here, but here's the method of elimination. Usually people just call this elimination. Our textbook actually calls this elimination by addition, but it's the same thing. It's the method of elimination. And the goal behind elimination is to add your equations together in such a way that you eliminate one of the variables. And once you've eliminated a variable, then it becomes very easy to read off the solution set of the system. So this is our goal. We're going to replace the original system of equations by an equivalent system. What do I mean by equivalent system? Formally, I mean by a new system of equations that has the exact same solution. So I'm not changing the solution set. If a solution exists, we'll end up with the same solution. So here I just mean same solution set. So even though I'm going to change what my equations look like, my solution set remains unchanged. And we're going to replace the original system of equations by an equivalent system that's easier to read off the solutions of. And our equivalent system should be so that when we add two of the equations together, we're eliminating a variable. Once we've eliminated it, then it's very easy to read off the solutions. And there's a few rules for how we can do this, right? We can't just replace our system of equations with any old other system. We have to sort of follow rules in how we obtain this equivalent system. And our rules are the following. One is I can interchange any two equations in the system. This one's fairly obvious. Of course, it shouldn't matter what order I write my equations in, right? I can rearrange the order of the equations. It doesn't change the solution. So number one is fairly obvious. Two is I can go into any equation and I can multiply or divide each side of the equation by the same non-zero constant. And that again shouldn't be very surprising. If you take an equation and you multiply or divide both sides by the same non-zero constant, you haven't really changed the equation at all. So number two isn't very surprising. But number three is here I can replace any equation in the system by the sum, or difference, we can subtract, but by the sum of that equation and any other equation in the system. Or in fact, I can do even more. Instead of adding to any other equation, I can add the sum of that equation and a non-zero multiple of any other equation in the system. Because remember, I can multiply equations by non-zero multiples on each side. So this is a sort of, this is the big one here, is we can add or subtract equations together. And moreover, I can multiply equations and then add or subtract them. And it turns out that doesn't change the solution set either. So how about we just do some examples? So here's my system. System with two equations and two variables. 2x plus 3y equals 1. Minus x plus y equals minus 3. So of course I know I could solve this already using substitution, but we're going to use the method of elimination here. And I'm going to start introducing some notation that we'll be using in future sections. So instead of calling these just equation 1 and equation 2, I'm going to call them R1 and R2. R really standing for row. So think of this as row 1 and row 2, but it's equation 1 and equation 2. And the goal here is to add my equations together in such a way that I eliminate a variable. So I can do this all in one step right now, but I'm going to do 2 steps just to make it more clear. What happens if I add the second equation to the first one? Well, I would end up with 2x minus x gives me just x. So I haven't quite eliminated x, but if I multiply this equation by 2 first, then I'll have 2x and minus 2x. So let's do this. Let's multiply equation 2, which I'm calling R2 by 2. So let's see, this is going to give me 2x plus 3y equals 1, and minus 2x, multiply this entire second equation by 2, minus 2x plus 2y equals minus 6. Remember to multiply both sides by 2. And again, the notation we'll be using in future sections, let's just start keeping track of this. I've taken equation 2, R2, and I've multiplied it by minus 2. So the notation I'll use is I'm replacing R2 by minus 2R2. So this is sort of this is the new row 2 is going to be the old minus 2 times R2. So there's the notation we'll be using in future sections. This is how I keep track of this, right? So R2, our new R2 in this line is minus 2 times the old R2. Okay, so now I'm going to add R1 and R2 together. Why am I doing that? Well, because this is the method of elimination, and I'm trying to eliminate this variable x. So what I'm actually going to do here is, maybe I shouldn't have phrased it this way, add R1 and R2 together, but I'm going to take R1 plus R2 and make that my new row 2. Okay, so I've got 2x plus 3y equals 1, and as a row 2 I'm adding row 1 to it. So add row 1 to row 2, and I've got 2x minus 2x is 0. Hence elimination, I've eliminated x from this equation. 0 plus what do I have here? 3y plus 2y is 5y. is equal to minus 6 plus 1 is minus 5. Alright? And now there's nothing much else that I have to do. You can see that by eliminating x, the equations or the solutions are sort of staring me in the face, right? If I have 5y equals minus 5, well that means divide both sides by 5. That means y is equal to minus 1. And if I back substitute that into this first equation, I should be able to easily solve for x. Right? Y is minus 1. Back substituting into the first equation, 2x plus minus 3, 3 times minus 1 equals 1. So 2x is equal to 4, adding 3 to both sides. So x is equal to 2. And there's my solution. I have a unique solution. My solution is x equals 2, y equals minus 1. And once again, you can always verify that your solutions are correct. Let's try and plug them in. X equals 2, y equals minus 1. I've got 4 minus 3 equals 1. Great. That's true. And minus 2 minus 1 equals minus 3. That's true. Great. So I've verified that this solution, we didn't make any mistakes, that this is indeed the correct solution. Right, so the goal here was to eliminate a variable. I could have also eliminated y. I could have multiplied the third equation by 3 and then subtracted the first equation from the second one. Right, that would have eliminated y, but we chose to eliminate x instead. So we multiplied the second equation by 2, and then we added the first equation to it, and that eliminated x. So in a nutshell, this is the method of elimination, is sort of modifying your system in such a way that your solutions become easy to read off. And once we've eliminated the variable, it was very easy to read off the solution. Alright, let's do another example. Alright, so here's another system. 2x plus 6y equals minus 3, and x plus 3y equals 2. Again, I want to eliminate a variable. Let's just focus on x. I could eliminate x from equation 1 by subtracting twice times row 2 from row 1. Right? So we're going to do row 1 minus 2 times row 2, and that's going to become our new row 1. Right? So I've still got row 2 is the same, or equation 2 is the same. X plus 3y equals 2. But row 1, I'm subtracting twice the second row from it. Again, in the first example, I did this in 2 steps. I would have said, okay, let's multiply the entire second equation by minus 2, and then we'll just add them together. Here I'm doing this all in 1 step because we're allowed to do this as well. We're allowed to add or subtract multiples of a row all in one go. So if I subtract twice the second row from the first one, we've got 2x minus 2x is 0. Oh, and then this is interesting. 6y minus 2 times 3y, so 6y minus 6y is 0. Equals what? I've got minus 3 minus 2 times 2. Minus 3 is, minus 3 minus 4 is minus 7. Right, or in other words, just writing this in a slightly nicer way, how about we interchange the order of these rows? X plus 3y equals 2. And 0 equals minus 7. Well, look at this second equation here. 0 equals minus 7. For what values of x and y is that ever true? For what values of x and y does 0 ever equal negative 7? And the answer is it never does, right? This, that's impossible. That's an inconsistent statement. So the answer is that, in fact, this system has no solutions. And not every system has solutions, right? Remember, if 2 lines are parallel, they never intersect, so there's no solutions for the system. And you can sort of see that that's exactly what's happening here, right? If I multiplied the second equation by 2, I would have 2x plus 6y. Well, these coefficients here are the same in both of them, that tells me they are parallel lines. These two equations have the same slope. So they are parallel lines, and hence we have no solutions at all. So if you come across this, a system like this, if you have no solutions, you'll end up with something like this after doing elimination. You'll end up with something like 0 equals -7, or just some sort of impossible inequality here. So last example that we'll do, here's one more system, 2x plus y equals 4, -6 minus 3y equals -12. Once again, you can sort of see that when I multiply the top equation by -3, we're going to have the same coefficients in front of x and y, so these two lines will have the same slope. But it turns out that we're not going to have this 0 equals -7 thing happening. We're actually going to end up with 0 equals 0, because although these two lines have the same slope, they're parallel, they actually coincide. They lie right on top of each other. They are, in fact, the same line. So let's see. If I want to eliminate a variable, how about we do this all in 2 steps again, because it's a little bit easier mentally to see what's happening. Let's say we multiply the first equation by 3. Alright, so we're going to do 3r1 is going to become our new r1. So that gives me 6x plus 3y equals 12, and minus 6x minus 3y equals -12. And now we'll just add them together. So let's say we add the first equation to the second one. Alright, so r1 plus r2 becomes our new r2. I should write it in the opposite order. I'm taking row 2 and I'm adding row 1 to it. Alright, so there's our second step. And that gives me what? That gives me, first equation is unchanged, 6x plus 3y equals 12. And if I add the top equation to the second one, I've got 0 plus 0. So 0 equals 12 plus -12 is 0. So here I don't have this inconsistency. This is a true statement. And this tells me that the solutions are going to be any old solutions of just this first equation. Okay, so I've got infinitely many solutions in this case. And the way you usually write them is you say, well, how about I let x be, let x be some number. Say, let x be k. Let x equal k. Alright, so k is usually thought of as the parameter. So let x equal k. Let's solve for y. 3y equals minus 6k plus 12. Or dividing both sides by 3, y is minus 2. Minus 2k plus 4. So this means every single solutions are points, I can't write, there we go, points of the form. This is when I'll usually give my solutions as points. So x can be k. You choose the x value, x is k, and then y is going to be minus 2k plus 4. And any point of that form is a solution of this system. So for example, if you just say, I'm going to take k to be 0, then my solution is going to be 0, and minus 2 times 0 plus 4, 0 and 4. There's a solution to the system. You can plug it in and verify that it works. Or how about I take k equals 1. Well, then I get 1, and minus 2 plus 4 is 2. There's another solution. You could plug in k is the square root of 2. You could plug in k equals pi. You could plug in k is 1.8. But this is sort of where this parameter comes in. You specify the value for k, and then I know the value for y as well. And that gives us, of course, infinitely many solutions, because there's infinitely many choices you could choose for k. So this is typically what you'll run into when you see this system, a system that has infinitely many solutions. You'll run into something like this, where you completely eliminate an entire equation in the system. This no longer carries any interesting information, and you're just looking at 6x plus 3y equals 12 at this point. So you say, okay, I'm just going to let x be a parameter, and then I'll write down what y is as well. And this can happen. So I suppose that in the next section we'll jump into why I'm calling this stuff not equation 1 but R1 and R2, why I'm using this notation to keep track of what's going on, and it's because I would sort of want to get you used to already what we're going to do in the next section. So we'll move on to that now. Thanks.